So let's add a tiny bit more to this idea of why western boundary is preferred in the ocean. Uh, I hope it's very clear. Ocean has boundaries as opposed to the atmosphere, which has no boundaries. And as soon as you put boundaries and you try to move things in the rotating system, western boundary intensification happens because of constraints on mass budget and vorticity budget. Vorticity has to be balanced, mass has to be balanced. This is shown again with this cute little experiment where again this sloping surface, sloping bottom is created from the north to the equator, and we are again on the rotating tank. Every time you see north as a direction as opposed to the equatorial direction on the other side in a water tank, you create it by having this sloping bottom to create shrinking of the Taylor columns. So here there is a sink here and there is a source here, so the water is being introduced here and being taken out here. So there is no changing of the height other than of the water level other than the slope of the bottom itself. So you're still creating the Taylor column height changes. So you introduce the water here, you dye it along the way, and you can see that instead of the water just flowing directly to the sink, so water is being pumped in carefully here, it's being taken out here. And the tank is rotating again at 5 RPM or so. And you can see that the water begins to flow to the western boundary again, takes the western boundary, and then finds its way to the sink. Okay? What we did before was to have a sinking water here by introducing it at the bottom, and we saw it went west and south, and then we had interior flow, but this is done in a very different way, just to demonstrate that in a rotating system, beta effects, which is represented by the sloping boundary here, creates this western boundary intensification. Again, we call it western boundary intensification because the western boundary currents are narrow, strong, and shallow. Remember we said that the abyssal flow is so slow that you cannot measure it. That's true for the interior, but as we talked about Stommel, it is measurable on the western boundary because that boundary current is strong. So this is an incredibly nice lab experiment to show why in a rotating system certain processes get selected when you have the rotation rate change with latitude. In this case, we are representing latitude by a sloping boundary. On Earth, we are on a sphere that gives us a natural increasing Coriolis from the equator to the poles, and this creates many of the interesting processes in the atmosphere in the ocean. In the atmosphere, we had talked about angular momentum conservation problems and baroclinic instabilities at mid-latitudes, and the eddies that get generated, and the eddies that have to do work to move energy to the poles from the low latitudes. Here, ocean has boundaries and it experiences the beta effect in a very different way, and it does that by having western boundary intensification as opposed to the baroclinic instabilities. There are baroclinic instabilities in the ocean as well, but the processes are very different. You get vertical shears from wind forcing. You have stronger currents at the surface, for example. Currents get weaker, so every time you have a vertical shear, you have energy that can be generated out of that shear. You also have horizontal shear, barotropic instabilities. We haven't done much about instabilities, but these contrasts of beta effects in the atmosphere and in the ocean is something really amazing that you should at least understand from the physics point of view. The equations are already there, you can go back to them, but make sure you understand the physics of these processes because they are incredibly cute. Okay? So that ends this podcast on uh, western boundary intensification. We'll move to the next part and slowly move towards more about observing the meridional overturning circulation using tracers, and then the heat transport by the meridional overturning circulation. This is the big part of the meridional overturning circulation, which is another word for thermohaline circulation. Because there is upwelling, meridional flow, sinking, and back. So this is a meridional overturning circulation. We call that thermohaline circulation, global conveyor belt. They're all the same things, okay?